Um, Hello.
Yes, sir.
I'm ready whenever all of you are.
Hello.
Yeah. Should I begin?
Yes, sir. I guess we can start. So, good evening to everyone present here. Welcome to the fourth talk in the Faculty Talk series of SciTech. Today we have with us Dr. Rajaram Nityananda. So, Dr. Rajaram studied physics at the Vivekananda College at the Indian Institute of Technology in Chennai and later worked for the PhD degree of the Bangalore University in the areas of optics and crystallography at the National Aerospace Laboratory. After joining the Raman Research Institute in Bangalore in 1975, he worked mainly on theoretical aspects of astronomy such as image processing, gravitational lensing, and gravitational dynamics. In the year 2000, he moved to Pune as the Center Director of the National Center for Radio Astrophysics of the TIFR. He retired in 2013 and since then has taught physics to undergraduate students, first at IISER Pune and for the last 6 years at Azim Premji University in Bangalore. He is a fellow of the three science academies in India and has served as editor of the Physics and Astronomy journals of the Indian Academy of Science. From 2014 to 2017, he was the chief editor of Resonance, the Journal of Science Education, and has also written many articles on the topics in physics and astronomy for that journal. Welcome, sir, and over to you.
Hello everyone. I'm still not hearing any voices from the Trivandrum side. I might like to do that before I begin.
So it's all here, sir.
Hello.
Hello?
Yeah, can you hear us?
Are we audible?
Okay. No, I'm not hearing any of you. No, but this is not good, right? Should we fix this? I don't want to give a one-day talk. Tab. Okay. Can someone say something?
Yeah. Hello, sir. Can you hear us? Yeah. I don't think sir can hear us.
Okay, please say something then.
Sure.
Yeah. Hello, sir. Can you hear?
And we also take care of the independence and the celebration of the dance.
Yeah. Hello, sir. Can you hear us now?
Hello?
Hello. Can you hear us now?
Hello, can you hear me?
Yes, sir, we can hear you.
Hello?
Hello?
Hello, how is it now?
Yes, sir, you're audible.
Is usually conducted.
Hello?
Hello.
She's from IISER-TVM. So we have got both type of events. We have got inter events as well as intra events. Where intra events are for IISER-TVM events exclusively.
Okay. So sorry for the late start. This is on Radio Astronomy. GMRT stands for Giant Metrewave Radio Telescope. But I'm going to back up and talk of some of the optical principles, some of which are more than 100 years old, which go into the modern way of making pictures of the sky, which are used by radio astronomers. And having worked at the Giant Metrewave Radio Telescope in Pune till about 2010, naturally my talk will have a certain bias towards that, but I will certainly tell you more about the field as a whole. So here is an absolutely basic picture, and in fact I'm going to use the same picture to talk about both telescopes and microscopes. It turns out that they are actually dual to each other in some sense. So in a telescope, you have this objective lens, and you have, let us say, some point source which are just put on the axis. So you can think of a point source as producing parallel rays or producing a plane wavefront, and then the lens focuses to a point. And if the source is somewhere else in a different direction, then it focuses to a different point. So clearly, this is the device which converts direction or angle to position on some screen. Now, of course, you might have one more lens there to give you a convenient image, but that's just for convenience. In principle, if you just be catching this on a screen or on a photographic plate or on the retina of your eye, okay? And the conversion factor is very simple. Angle and radiance multiplied by this focal length is what you have, okay? Now, how does the microscope work? You just reverse all these rays, and then so the object is now here, the one you are interested in, the bacteria or whatever it is, and each point on that clears the direction. Now, again, for your convenience, you might have another lens to project it onto your retina or screen, okay? So that's the basic idea. And now let's talk of the resolving power. And this is something which is in the textbook called the Ryle criterion. So I'll touch on it briefly. The famous formula for a telescope is take the wavelength, divide by the diameter of that first lens which you saw, and that gives you the angle in radians. And if two sources are separated by less than this angle, the images overlap. Now, why is that? I can give a very simple explanation. So here you look at one plane wavefront coming from one direction and another plane wavefront coming from an angle theta. Okay. Now the first wavefront produces a bright image here, which means all these paths interfere constructively. Now suppose I have another source what Ryle asked is, we want to make sure that the light from that source will interfere destructively here. And the criterion for that is that as you move from here to here, these two wavefronts should differ in phase by about a wavelength. Right? So that means, although all these add up constructively, these will add up destructively, because starting at any point, the phase will go all the way through 2 pi and get it. So the Ryle criterion is that the two sources must be separated, right, by so that you get all phases from 0 to 2 pi at the position of the first source if you look at the second source, right? Now this can immediately be converted to a criterion for the microscope, right? So all that you do is take this small angle and multiply by the focal length. And that tells you the size of the object, which will produce two distinct images. By distinct we mean at the center of the first image, the second image has a null, zero intensity. Of course, these images are finite size, they overlap, but you can distinguish them. And notice for the microscope, if you have a length of a fixed diameter, you want to have as small a focal length as possible. See, when people say high resolution, they actually mean this quantity is small or this quantity is small, right? Small angles can be made up or small objects can be seen, right? So that's why you pay a lot for a microscope objective if this f/d ratio is very small, okay? Or if you go back to the figure, you'll see that f/d is nothing but that angle which is subtended, right? This is f, this is d, and therefore you want a large angle. And of course, making a lens which takes away from a large angle is complicated. Yeah? You pay a lot for it. Okay. Now, since I am talking one way, I'm just going to check that I have coming through so far.
Yeah, can you hear us now, sir? Yeah, but we can't seem to hear you right now.
Okay, I think now we are in two-way communication. Is that right?
Yeah, now it's fine.
Oh my God, that's a relief. I'm very sorry that it took almost half an hour to get to this stage. Huh?
Yeah, so your presentation was not visible till now.
Presentation was visible, audio was visible, audio was audible?
Yeah, audio was audible, but your presentation was not visible.
Oh, okay. Then I'm sorry, I'll have to backtrack. Huh?
Yeah, okay, sir. You can present now and we can start. I think it's fine right now.
Yeah. Okay. Oh, this is very sad. Don't know why. So that's why I did a test, but for some reason it worked. Yeah. So now I'm visible and audible. Hello.
Yes, sir.
Huh?
Yeah, both visible and audible.
Okay, great. Yeah. All right. So this is the title, and as I say, I'll be a little more brief. GMRT stands for the Giant Metrewave Radio Telescope. which is a major facility in Pune. I hope all of you have heard of it. And since I worked there for 10 years, my talk will, toward the end, spend more time on this telescope. But to start with, we'll talk about the principles behind all telescopes or all microscopes. Okay? And there are two ways of looking at it, which are both interesting. The first way is due to Rayleigh, which is there in all the textbooks, right? So you have parallel rays coming from a point source or a plane wave front getting focused at some point, according to geometrical optics. Now, according to wave optics, of course, you get constructive interference at this point because all the paths are equal. But if you tilt this incoming wavefront by some small angle, let's call it theta, then you could get destructive interference at this point. And the criterion for that is that the phase difference between this wavefront, which is in a solid line, is causing constructive interference here. So if this extra phase at the edge of the lens, going from this side to this side, is one wavelength, then you actually get destructive interference, because that's what happens even in a single slit, right? And so if you take these two objects, which are separated by this small angle theta, they will be resolved according to Mr. Rayleigh, Lord Rayleigh actually, because one of them creates image here, center is here, and the other image is centered here, but it has a null here. So you can kind of tell the two images apart. So that is Rayleigh. That angle is lambda over d, right? And this is just what I told you. And the interesting thing is the microscope can also be thought of this way just by reversing the rays, right? So, so now you think of this as the source, and that creates beam going this way. And if you move the source, in fact, this is a fundamental principle of optics, principle of reversibility, right? You can bring in rays from here, or if this is the source, then it will go back that way. Of course, microscopes usually have an eyepiece, but for your eye to be comfortable and relaxed, these rays should almost be parallel, right? Should go to infinity. Of course, then they will be focused again by some camera, but it will be magnified. So that's the importance of the diameter for a telescope. We'll mainly concentrate in telescopes. Yeah. You want, for the same wavelength, you have a large diameter, you get. But there's another beautiful way of understanding the resolving power of a microscope. And I had the name of this man, Abbe. It's not often given in the books, right? So he said, let's not think of the object is made up of point objects. Let's think of it as made up of periodic objects. Or since this is a physics society, you're not afraid of Fourier analysis. So this is like one Fourier component of the brightness of an object, something periodic. Then you have, let us say, this is illuminated by some light, and if light falls on a periodic object, that's a diffraction grating, right? And the smaller you make this grating, the larger this angle becomes. And if small d is now the separation of this grating, sorry. I'm sorry, I'm sorry, I'm in a meeting. I cannot take this call. Please tell. Right. So his point was that you have this grating. It creates a zero order and first order minus first order. Small d is the space separation. This angle is lambda by d, right? And the angle subtended by the lens is d over f. Okay. So you want to again get an image of this grating here, and you will only get that if you only let through this beam. You will just get a point. You won't get anything, right? You're illuminating the lens uniformly. But if you allow these beams as well as this one, they will interfere and create a periodic pattern here. So he analyzed the resolving power of a microscope, and same argument works for telescopes, in terms of Fourier components. So a given Fourier component in the object of the microscope creates diffracted beams at various angles, And the smaller this becomes, it becomes too small, you miss all the diffracted beams and you don't see anything. And he actually verified all this experimentally. Now, the reason to tell you about this is that if you just look at lambda by d, and now we're going to talk radio waves. Let's take lambda as 3 centimeters, for example. This is absolutely the biggest radio telescope there is. You might have all read about the collapse of the Arecibo radio telescope, right? That was the biggest till very recently. It had a diameter of 305 meters. And then our neighbors built a very similar idea to Arecibo, but with more modern technology. And this is 500 meters in diameter. Okay. So radio waves fall on it, they get focused. You can hardly see the object at the focus, but there is something hanging there, suspended by these towers. And but still, even 500 meters and 3 centimeters wavelength, which is the shortest wavelength they use, you will get the resolving power of the human eye, about 1 arc minute. That's not good enough, right? So a lot of the story today is going to be how radio astronomers managed to beat this. Okay. And actually, they got an idea from this great man, Michelson. Okay. So what this picture shows is this star Betelgeuse, which was also in the news because people thought it was going to explode, but it did not. Okay. And this figure is not to scale. These are 2 mirrors which are 6 meters apart, but the star is some 16 to 18 meters apart. Okay? So essentially, you have beams coming from the star, right? This is an ingenious arrangement made by Michelson. I'll show you a sketch, show you the real arrangement later. And the idea is to combine these 2 beams and look for interference fringes. And it's actually technically quite difficult. Now, what do you gain? If the star was a point source, of course you will see interference fringes, right? But as you make the star bigger and bigger, and Betelgeuse is one of the biggest stars, at some point you lose the fringes. And that's what I would like to explain. So the principle is like this. You have 2 mirrors which are separated by some B. Now, B is the jargon for baseline. And then this is the sky. So if, as I told you, you have a point source, let us say in this direction, then you get fringes, no problem. You get constructive interference, let us say at some point in the interference pattern. But now if I take another source moving away, so this is the sky far away. If I move a certain distance, which is just lambda divided by b, half of that. If I go by an angle of lambda by b, again I'll get constructive interference, right? Because now there'll be a phase difference of lambda. But in between, you have this dashed line, which is a direction where a source will produce destructive interference, right? So this set of arrows is supposed to convey the idea that different points in the sky will produce constructive and destructive interference. Now, suppose the object is big, like big, then different parts of it will produce constructive and destructive interference, and you will not see fringes. So this is the beautiful idea of Michelson, that a point source produces fringes, and an extended source, of course, it all depends on the value of B, right? If B is very small, then this angle would be large, right? And therefore, you will still see fringes. So he needed to make B larger and larger, and he kept making B larger and larger, and then at a few meters, Betelgeuse stopped giving fringes. So he was able to measure the angular size of Betelgeuse. And here is a bit of the mathematics involved. Huh? So B is brightness, capital B. It's a function of angle. Huh? So you have some brightness, which is the function of angle. For a simple thing like a spherical star, it would just be a constant in some region and 0 outside. Now, I'm just concentrating on the interference term in the fringes, right? Fringes, of course, intensity is positive everywhere, but you subtract the average intensity, then that is what tells you what the fringes are. And then you have a cosine, and you can easily see I have just fixed up whatever is sitting inside the cosine, so that if lambda, let's say, right? So at this angle theta, this is the kind of phase which you will get, phase difference which you will get. Okay. 2 pi by lambda, and b times theta is the path difference. Okay. If something comes along the axis, 0 path difference. If it comes at an angle theta, b times theta path difference, convert it into a phase difference, right? So basically, what Michelson was doing, he was not a very mathematical physicist or astronomer, or whatever you like to call him, but he wrote down this formula. Of course, you recognize it as like computing the Fourier transform, cosine Fourier transform of b of theta. So now let me show you the modern. So this is the way Michelson did it. So this is a 2.5 meter telescope on Mount Wilson, but he wanted more than 2.5 meters. So he put this beam on top, and these are the two mirrors. So they combine the light from here, comes somewhere here, goes down, actually comes back up from the mirror. And believe it or not, Michelson sat here in the cold and observed the fringes. But today life is more comfortable. So on the same Mount Wilson, this is the same telescope that Michelson used, but scientists from Georgia State University have now put all these small telescopes. You can see some 6 of them, maybe one here. And of course, they're using all modern technology. So the light from these telescopes is then combined by means of some vacuum tubes, a lot of very sophisticated electronics, servo systems, optics. So now they can increase B to 330 meters. So this is the modern version, and it has been used brilliantly to study stars, not just Betelgeuse, right? So if you want to look up more, please look up CHARA. So although I have worked more in radio astronomy and my loyalties are there, but I thought I should begin by telling you how this area has been used by optical astronomers. So the resolving power now, today, to study the disks of stars corresponds to 330 meters. But now let's continue. Now this is a remarkable idea, came in Cambridge, and it won the Nobel Prize for Martin Ryle. Okay, and I'll tell you more about it. So he built a railway track in east-west direction. So you're now looking from the North Pole, and this is the equator. So Cambridge is somewhere here, and of course this is exaggerated, right? He built something called the 1 mile telescope. He built many telescopes, but so here are 2 antennas. So we can use the same argument that we used earlier. So this part of the figure is the sky. So, and again, we use the idea of reversibility. If you think of these 2 telescopes as transmitting radio waves, they will create fringes in the sky. A central fringe, which is at the point direction equidistant from the 2 telescopes, bisecting the 2 telescopes. And then another fringe when the path difference is lambda, another one is, so on. Right? Now, using the idea of reversibility, if you have some object in the sky, different parts of the object will give you constructive and destructive interference, and you will get this Fourier transform. Now, it's not very useful to get the Fourier transform for one value of B, right? You need all values of B if you want to reconstruct the object. So for that, 2 beautiful ideas. One is put these on a railway track, and you measure the Fourier transform patiently by moving one of the telescopes to all positions. The second is, when you keep 2 telescopes at some fixed distance, wait for 12 hours. Okay? Then these fringes will rotate because the Earth is rotating. So that is the way that Ryle was able to find not just one point on the Fourier transform, but all points on the Fourier transform up to some maximum value. Right? So certainly I have to show you a picture of this great man. Here he is, his telescope. He deservedly won the Nobel Prize in 74. But he demonstrated this technique and of course did some beautiful astronomy with it as well. So a little more detail on this technique. It's called aperture synthesis, because the final result is, as I told you in the case of Michelson also, getting what you would get from a very large telescope, but using only very small telescopes, right? So So now I have changed the viewpoint. We are looking from the equator, not from the pole. So this is the equator, that's the North Pole. And it's not that radio astronomers only study the North Pole. Okay. So here are two telescopes. This is some patch of the sky. So the Earth and the sky are both shown on this picture. This is the so-called celestial sphere. So it's really very far away from this. And these are the fringes produced by these telescopes. And as the Earth rotates, you can see the fringes rotate. But as you move the telescopes, you can again see you can get finer fringes. So, so really the Fourier transform is in 2 dimensions. There'll not be too much maths on this talk, but I thought I should show you the basic result, fundamental result. So this is the electric field coming from some direction, kx, ky. And xy are points on the ground. Right? And this is just the famous formula for a plane wave. And this is the amplitude and phase of the plane wave, right? The complex number. So now if you multiply, okay, yeah, can you see this? Yeah. What you want to know is the intensity of the brightness or the energy coming from this direction, kx, ky. So you are squaring this, and then if you do some simple algebra, if you square this, when I say square, I mean take the complex conjugate and multiply. You will get this kind of quantity, right? You will get E at xy and the complex conjugate, which means you're taking the phase difference at a displaced point, x plus u, y plus v, right? So that's exactly what you do when you interfere two telescopes, right? This is the interference term, okay? So that's a bit about the mathematics. I can say more if people are curious. But now let's see how this theme was developed. So the further progress took place quite rapidly, actually. And one of the telescopes which was built, and now Ryle himself had small limited funds, even though he was a small country and a small university. But of course, it was he who got the Nobel Prize because he had the idea first. But once he had the idea, the people in the US built a magnificent telescope, which I'll show you. It's called the Very Large Array. So they by 1980 this started functioning, and it has been functioning beautifully ever since, and it has continuously improved. Of course, the antennas remain the same, but the receivers, the electronics, of course, progresses greatly. And once you have this Fourier transform, your information is still incomplete because you do not, in the case of very large array, you are able to separate the telescopes up to 30 kilometers, again on railway tracks, okay? But still there will be gaps, right? So a whole science has developed, and that's something I have also done some work, so I can tell you more about it. Suppose you have incomplete information on the Fourier transform, can you still make an image? So that's like making an image with a broken mirror or a broken lens, okay? Can be done. But that's not the whole story. Any lens has aberrations. In this case, of course, you can make your telescopes perfect if you like. But there are phase changes which occur in the ionosphere and the atmosphere. You may want to correct for them and can be corrected. And then the other fantastic progress in radio astronomy came when people realized that you don't have to, whatever I showed you on the previous slide, taking the electric field at one telescope and interfering it. See, interference you normally think of as taking A plus B and squaring it, right? But of course, A squared and B squared, there's no interference. That's the intensity of each telescope. So it's the 2AB which really tells you the interference. So the idea here was that you record the electric field at each telescope and you take these tapes to a common point and you can multiply them later. This is during, sorry, misspelling. So this technique is called very long baseline interferometry. Okay. So here is a picture of the VLA. I mean, this looks like just a few kilometers, but believe me, this railway track keeps running for 30 kilometers. It's a remarkable location actually. And there are 27 antennas and all, you can count them. And here's another picture, close up. really beautiful. And this technique of separating antennas in different places was pushed to the extreme in an event which you would have all heard of in 2019. Something called the Event Horizon Telescope. It's not a single telescope. There are two institutions which led it, but maybe dozens of institutions that took part. So Center for Astrophysics in Cambridge, but Cambridge in the United States. And Max Planck Institute for Radio Astronomy. So this telescope had antennas as far apart as Hawaii, Spain, somewhere in the United States, right? This is Chile, and this is even the South Pole, right? So these are pictures of all these antennas. Now these were built for a different purpose. They were built to do astronomy at millimeter wavelengths. So 2.6 millimeters happens to be an important wavelength because the molecules of carbon monoxide emit and absorb at this wavelength. And carbon monoxide exists in objects called molecular clouds. Of course, carbon monoxide is not the main ingredient. The main ingredient is H2, molecular hydrogen. So these are the places where the gas is very dense, but H2 doesn't show up in radio astronomy. Carbon monoxide does, for good physics reasons. One has a dipole moment, other doesn't. And then, if you can study these molecular clouds, you can study the places where stars form, planets form, and so on. Very important. But since these telescopes were there at a very small wavelength, these enterprising people from Max Planck and so on said, so they persuaded the owners of all these telescopes, so many different observatories, to install this sophisticated recording equipment. And they carried out this experiment sometime in 2016. But if you record a signal at the South Pole, I mean, first of all, imagine taking, and this is not your ordinary tape recorder. This records at 16 gigabytes per second. Okay. Because remember, the wavelength is really short, right? So the frequency is high, hundreds of gigahertz. So anyway, to cut a long story short, they combined all these, it took them 3 years to take these recordings, calculate whatever I told you on the previous figure. That is, do this kind of virtual interference, right? And then produce an image. And this is the image. And the important point is that the angular resolution of this image is the best ever achieved in astronomy. In spite of the fact that this wavelength is, of course, much longer than what optical astronomers, X-ray astronomers use. But these people, I mean, their lambda, they couldn't reduce beyond a point. But their D was as big as the Earth would allow. So you can work out what lambda by D is. It's really an amazing achievement. And they needed it because this is matter very close to a black hole. And it's emitting radio waves. And it's not uniformly bright. So this is regarded as observational evidence because this is really like a shadow, or the radiation really has fallen into the black hole here, so to speak. So now I want to sort of make it more India-centric. So we have to backtrack, where a major effort started in 1970, and the man behind it is Govind Swarup, whom again many of you may have heard of, especially because he passed away recently, and the media did say quite a bit about his contributions. So his first idea, and of course he assembled a very young, enthusiastic team of people to do it, was used a technique. It is interferometry, but of a strange kind. So this is supposed to be the moon. Okay, this is my sketch of the moon. These are rays coming from some faraway radio source. Normally, of course, if you think of this plane wavefront, it gets cut off by the moon. So it's like diffraction by a straight edge. That's one way of thinking about it. But the other way of thinking about it, which is also legitimate, though it's not given in textbooks, but it goes back to Young himself, Thomas Young. He said, I can understand the diffraction pattern of a straight edge as interference between this ray and a ray coming from this edge. So what happens if you go into the shadow? Then you get only this one. You don't get that. So in the shadow, you don't see any fringes. But when you come here, this edge wave interferes with this wave and gives you fringes. But it's interesting that those fringes are not equally spaced in theta. If you look at the geometry of this figure, the path difference is now d into 1 minus cos theta. You can see that, which is approximately d theta squared. So the fringes are equally spaced in theta squared. And also they get weaker and weaker. But basically you can do this kind of interferometry on sources simply by having a single telescope, but waiting patiently for the moon to cover up. Of course, that's not what Swarup and his colleagues did. They just followed the moon, and every source that the moon covered up, which was bright enough, they created maps of it, simple maps. Yeah. Right. So, a lot of things happened at the OT radio telescope, but this was the major program, lunar occultation. But having built such a big telescope, they did other very interesting things with it. Okay. So now, I'm sorry, I'm running a bit fast because of the lost time. I've come to the GMRT, Giant Metrewave Radio Telescope. That's a project, as I gave you a rough date of 1970. The project was started around 1965, but it took 5 years to. Now, in the case of GMRT, the project was started around 1989, but it took nearly 10 years for it to achieve its full capability, though very useful work was done even before that. So now you can see that VLA idea is being used of having the telescopes on 3 arms. Okay. So even without Earth rotation, you will get quite a lot of baselines. In fact, GMRT has 30 telescopes. So you can do 30 into 29 divided by 2. That's the number of values of B which you get. And sometimes that is enough information to tell you about the source. If it's not, you do Earth rotation, right? This is Narayangam. It's a town between Pune and Nashik. And this is a small village, Khodad. I think the people who built the telescope practically lived here. And even I used to go there once a week, right? So there are actually some lots of antennas here. And then these antennas, they go up to about 25 kilometers separation. Now, it is not practical to build railway lines. Okay. So that freedom one had to lose. So, but still remarkable work could be done. So here is a nice panoramic view. You can see almost 11 antennas here. And the word giant is appropriate for 2 reasons. One is that you have 30 antennas, and each antenna is 45 meters in diameter. The VLA was 25. Okay. But it operates at meter wavelengths. See, the VLA can operate down to wavelengths of almost a centimeter. Whereas this was deliberately designed to work at long wavelengths. And you'll see why. One is, of course, the whole world was doing short wavelengths. So obviously, Govind Swarup and his colleagues did not want to do the same thing as the rest of the world. They wanted something new, something different. So here is a close-up of one of the antennas. And believe me, they're really beautiful. And they do welcome excursions with prior notice. I strongly, once all these lockdowns end, I strongly urge many of you to go there and take a look. Incidentally, now that we're taking a close look, it can operate at many different wavelengths, and receivers for those wavelengths are mounted on some rotating table. So you have to rotate and point the right one to the dish. Now, the one thing you might be wondering is, how is this reflecting radio waves, right? You're looking right through it. But actually, there are wire mesh here. So the general idea is that if the wavelength is, the shortest wavelength here is around 20 centimeters, but these wire meshes are 1 or 1.5 centimeters apart, or maximum is about 2 centimeters apart, right? So a wavelength of 20 centimeters sees this as a continuous reflecting surface, but your human eye looks right through it. And the idea of using wire mesh, of course, is to reduce the weight and also reduce the force with the wind exerts. So for its size, this was one of the most inexpensive radio telescopes ever built. And the design was completely unique. You notice most telescopes have a heavy structure behind to keep the telescope geometry in place. This does not have that. So Govind Swarup called this SMART, S-M-A-R-T, stretched mesh attached to rope trusses. So again, you don't see, there are lots of ropes here. behind, which hold this into a parabolic shape. So here is a young Govind Swarup. Okay, it's taken in Australia, I think, or in the US, where he got his early training in radio astronomy. And of course, he came back in 1963 and started this. So a little bit about the science at these places. Okay, so at Ooty, they measured the angular sizes of faint and faraway radio sources. Again, the same principle. If the source is too large, you lose the fringes. And depending on the strength of the fringes, you can see what the size of the source is. But this is not just to make a catalog. The idea is that if the source is faint, it's very far away. And you would like to know, are the properties of those sources the same as the ones which we see nearby? Or, so this was doing cosmology. Then, for the rest of the time, when the moon was not up, they used another interesting tool which also tells you the sizes of radio sources. It's called scintillation, which is just a technical optics term for twinkling. Okay, and twinkling occurs for stars because beautiful parallel rays and plane wavefront hit the top of the atmosphere, get distorted by refractive index irregularities in the atmosphere. Okay, and therefore the intensity on the ground is not uniform. Right. In fact, you can even check that the intensity at your two eyes is not uniform. If you look at a bright star by crossing your eyes, you'll see two images and they will twinkle differently. Now, in the case of, but again, the same thing, if the source is too large, the twinkling goes away because different parts of the source pass through different parts of the atmosphere. Okay. In the case of radio sources, this is not the Earth's atmosphere, but it's something called the solar wind, plasma which is blown out from the sun. And therefore, you study the solar wind and you also study the sources. Then, at a wavelength of 1 meter, you would be surprised to know, can a hydrogen atom or a similar atom emit? And the answer is yes, if you make n large enough. So, one of my colleagues at the Raman Research Institute did a PhD thesis, and later on there were more theses from the Ooty group. If you take n equal to 274 to 273, you can work it out. You will get a wavelength of around a meter. Okay. So you can actually measure a spectral line, and then the moment you do that, you know what it is, what the object is, you know also at what speed it is moving because of the Doppler effect. Okay, so you can do interesting astronomy. Then the frequency of the Ooty radio telescope was chosen as to be 327 megahertz. So it's not really 1 meter, it's more like 92 centimeters. And that was chosen because deuterium, which is the rarer form of hydrogen, right? Emits and absorbs at that wavelength. We'll come to that. But of course, they did not detect deuterium, but it's still interesting to know the abundance of deuterium again has significance for cosmology. And in 1967, pulsars were discovered, and that's a whole subject in itself. Okay? And rather than give you some very hurried account of pulsars, I would strongly urge you to contact some of the many people who work on pulsars. I can suggest names if you like, who can tell you more about that. So I want to focus on hydrogen. So this is the blow up of the hydrogen atom. So this is the proton, which is really big. Okay. And this is the magnetic field of the proton because it has a spin, it has a charge, it has a magnetic moment. This is mu of the proton. Then you have the magnetic moment of the electron. So these two magnetic moments are going to interact. So the electron is in its ground state, okay, which means its average distance from here is about 0.5 angstroms, right? Which is of course much larger than this. The distance is the Bohr radius. So if you put two magnetic moments separated by a Bohr radius, their energy can be attractive or repulsive depending on whether they are parallel or anti-parallel, right? So this formula you might have well seen in your high school, right? So you can just work this out and you will get a very small energy. So really what you call the ground state of hydrogen is 4 states because the proton has 2 spin states, the electron has 2 spin states, right? So you get 4 states in all, and you might even have studied, you combine them, you will get 1 state in which they are anti-parallel and 2 three states in which they are parallel. Okay, so those are split apart. So these are the parallel states, three of them actually, and the frequency separation is about 1.4 gigahertz. In terms of temperature units, is 50 millikelvin. So which means at any reasonable temperature, both levels will be occupied. It's some micro electron volts, but the wavelength is 21 centimeters. Okay, so this is the way the radio astronomers started after 1950, studying cold because it's in the ground state, neutral because the electron is still stuck with the proton, diffuse, so it's spread in large gas clouds. Oh, I've got neutral again. Atomic hydrogen. It's not molecular. Molecular is a different story because the two spins of the electrons will cancel. You don't want that. You can study it in interstellar space in our galaxy. That's what was done first. And then people started studying it in the space in between the galaxies. And the whole idea is to study these gas clouds from which you form stars, you form galaxies and so on. So one of the major themes of astronomy, radio astronomy in this case, it's called H1 for some funny reason, which I can tell you about. So, the main thing which Professor Swarup and the whole group, and now they were not the UTI group anymore, they were the Pune group, they were called the National Center for Radio Astrophysics, NCRA. I guess I should say we. I just don't want to say we because I didn't help them in this period at all. I didn't contribute when they were building the telescope. The whole idea is that if it's at a cosmological distance, you won't get it at 21 centimeters. You will get it at longer wavelengths because the universe is expanding. Right? So that was the virtue of going to meter wavelengths. And the advantage which they had over their colleagues in more advanced countries was that that part of the electromagnetic spectrum is heavily used by man-made activities in all advanced countries in the world. So that's why they went to shorter wavelengths. But this group could go to longer wavelengths. At least when they built the telescope, the amount of interference from man-made activity was somewhat lower. So GMRT was used to study neutral hydrogen at cosmological distances, and also in dwarf galaxies. These are very small galaxies, but they're very interesting because they seem to have not formed many stars, and therefore they're in the same condition as when they were formed. So you're really doing cosmology by studying a very small galaxy. Pulsars, huge subject. And look, the telescope was completed 2000, so it's 20 years now. A lot of nice studies of pulsars, discovering new ones, taking existing ones and studying the emission. Emission is still not fully understood, but a lot of details have been worked out. And the other thing, which is in a way similar to what was done at UTI, you survey the whole sky and you make a catalog of sources and then you try to extract cosmology. So that is one of the major projects. Individual sources are interesting, you can follow them up, and many interesting sources are there. Then you have something explodes, a star explodes. Initially you see it as a flash of light, and then the material which is ejected collides with the surrounding material, starts emitting radio waves, and there are young people, in fact a young lady, Poonam Chandra, who has followed them for years. They tell you a lot about the supernovae. Then these are some mysterious objects called magnetars, which every now and then will emit pulses and then stop. So, in fact, the GMRT is used by people from all over the world. Every 6 months, they receive proposals from anywhere, which give the scientific justification and also technical justification. You should get useful results using the capabilities of GMRT. And these are refereed by a committee. And they allotted time. In fact, the first thing people used to ask us is, do you charge them? The answer is no. Yes, we charge them for the vada pav or something, we serve them in the canteen, but otherwise it's free. They come, but of course, there's the big barrier. And suppose there's something really urgent, like, a supernova has exploded, then you can't wait 6 months perhaps. You want to see the radio emission might decay in days. So then you go to the NCRA director, which was me for a while, and then you make a proposal for what is called director's discretionary time, and many interesting things were done in this. Sorry, this is just a snapshot. So I'll just give you two examples. So many of you may know that bright galaxies have NGC numbers. This is not such a bright galaxy. In fact, if you look at it with an optical telescope, this is all that you see. Okay, this tiny thing here. So it is thought to be a dwarf galaxy. But when and the world expert in dwarf galaxies is Igor Karachantsev from this observatory in Russia. And Rajaram is faculty member. Aisha Begum was his research student at that time. And they looked at from 60 dwarf galaxies, in fact, right? And this one turned out to be a giant galaxy. But all this hydrogen which is sitting there was rotating around this, but it was not forming stars. Okay. And by looking at the rotation, you would also say that the attraction of these stars is not enough to keep these, to balance the centrifugal force. And therefore, there is some dark matter. Of course, dark matter in galaxies has been known from the 1980s. But in dwarf galaxies, it has a lot of extra significance. Now, the dream of building the GMRT was to look at hydrogen at really large distances. For example, when 21 centimeters have become 42 centimeters, right? That is what is called redshift of 1. So redshift is some quantity called Z, and increase of wavelength is 1 plus Z. So Z is 0 is no increase nearby. Z is 1 is, this is 40 centimeters. Now this frequency is very difficult to observe anywhere in the world, but GMRT is ready to do it. And this tells you that they have detected that hydrogen. So that means, and this is redshift of 1 means it's billions of years back. So what is the properties of galaxies at that time are now being directly studied. But I have to tell you something about this picture. This is a spectral line, right? You notice this is 740 megahertz. Now, this axis is calibrated in velocity because the width of this is due to the Doppler effect. All the hydrogen is not moving at the same speed. But there is something peculiar about this picture. And I have to, about this spectrum. And the best way of illustrating that is this. How many of you have seen these two people? Sorry, am I audible? I just thought I'd take a small break and ask you whether this picture makes any sense.
Yes, sir, you're audible.
So do you know who this is and who this is? Okay. The answer is very interesting. The answer is no one. Okay. So what people did is they took pictures of some very large number of Indians. Okay. Male and female, roughly at the same age, of course. And then they, of course, took various characteristics like the dimension, this, that, the other, ratios. And they had to scale the pictures suitably. And then they superposed them. So this is an average picture of young Indian. And this is an average picture of young Indian woman. So this is an average picture of 7,000 galaxies. So pointing the telescope to any one galaxy, by the way, you don't observe only one galaxy. You observe all the galaxies in the field of view because of aperture synthesis, right? Now each individual galaxy, it's not detectable at all because it's too faint, it's too far away. So they had to do something similar to what this picture was. That's called stacking. And this is really a very recent paper. Appeared on October 14th in Nature. Chaudhary is, I think, the research student and the whole collaboration. So it's the first detection of hydrogen, and this is something really to be proud of, right? GMRT came with a lot of technical innovations also. And these innovations were recognized by the Institute of Electrical and Electronics Engineers, IEEE. Right? So IEEE has taken, in each country, they identify milestones. So in India, there were 2 milestones, and their view of electrical engineering is very broad. Anything which is scientific, but which has also got a lot of use. So the previous 2 milestones were Jagdish Chandra Bose, who in the 1890s actually produced millimeter waves. I hope all of you know that. We all know the names of Marconi and Hertz and so on. But J.C. Bose produced these millimeter waves at the same time as these people. And a little after Hertz, of course. But so that IEEE recognized as a milestone. The second they recognized is 1928, the Raman effect. So their idea of radio waves includes visible light. The third milestone is the construction of the GMRT. Okay? So the technical innovations, I told you about the smart antenna concept. In the VLA, they actually brought the signal in, Ryle brought in the signals to the common point by cables. VLA used waveguides, but GMRT is one of the first to use optical fibers. Okay. Govind Swarup had a very limited budget. So he squeezed his engineering colleagues and his science colleagues to get the maximum. So every one of the systems which you see, which rotates the different fields, which the optical fiber, even the building, the antenna, everything was controlled. So by the way, I didn't tell you one thing, the antenna is unmanned. Okay. So all the control is done remotely over these same optical fibers. And all these systems were really built. Of course, some help from, after all, NCRA is part of TIFR, which is part of Department of Atomic Energy, which controls things like reactors. So the reactor control people built initially the few prototype systems, but ultimately the engineers at GMRT had to adapt them to our own use. Okay. So I thought I will end just by, giving you, this is a citation. It will appear on the IAU, on the IEEE website. And you can read it. It tells you all the things I've told you. Pioneered new techniques in antenna design, signal transport. So let me stop here and give some time for discussion. Okay.
If one of you has some questions regarding, you can unmute your mic or put it in the chat. Yeah, so there's a question in the chat. Can I read it out for you? Can you explain?
I saw it's a very good question. Okay. Sure. Yes. So let me now switch to something where I can draw a small sketch. It'll take me a minute to do that. Okay, but I'm not presenting. I should be presenting. Present the entire screen. Share. Yeah. See, if you ask why does a metal plate reflect radio waves, right? So here's a metal plate, and here are some radio waves coming onto it. The radio waves have an electric field, yeah, and the electric field produces currents parallel to the electric field. This is E. Now these currents act as a source of radio waves. So they produce the reflected wave. And what is very interesting, and which we never tell you in the optics course, but it's completely true. So this is the original source, and this is the reflected, right? Now you don't see any radio waves behind us. Now normally the usual way we are taught is everything is reflected. But that's not really the right way to look at it. The right way to look at it is there are some charges moving in the source, they produce waves. There are some charges moving in this plate, they also produce waves. Okay? And when you sit at a point here, you will see the waves produced by this source. You will also see the waves produced by this sheet. Okay? And the amazing fact is that you see zero intensity here because of destructive interference between what comes from the source and what comes from all the currents induced in the sheet. Okay? Currents, in this direction. But those same currents produce the reflected wave. So this sheet radiates in both directions, it produces a reflected. Now, instead of a sheet, suppose you have a set of wires. It is still true that if the electric vector is polarized this way, right, it will produce currents, but this time the cancellation will not be perfect on this side and the reflection will not be perfect. But if you have more wires, you get perfect cancellation, you go towards perfect cancellation. And the general criterion is that the spacing between the wires has to be significantly less than the wavelength. So in UT, for example, I think the spacing was, let me see, it was about 3 centimeters in UT, the separation of the wires, but the wavelength was 90 centimeters. So that was very comfortable. In GMRT, the shortest wavelength was 20 centimeters, and the largest separation was, well, the inner part of the dish had 1 centimeter and the outer part had 2 centimeters. The other peculiar thing you notice is, if the radio wave is polarized this way, yeah, then it cannot produce currents in a wire which is in this direction, because this is an insulator, right? So actually this polarization comes through completely. So UT radio telescope only saw one polarization. However, GMRT sees both polarizations because it's a mesh. So if you look at the wires, so any polarization gets resolved into these two components. And so the reason why, so actually 1/10 is not, actually does transmit something, but Professor Swarup was working on a limited budget. If he had made this smaller, then the weight would have gone up and everything would have gone up. So I hope that kind of answers the question. It's still a very interesting problem in electromagnetism, to work out the scattering by a single wire and then work out the scattering by a bunch of wires. And the answer is what I told you. Yeah. Stop presenting. Yeah.
Yeah, so there's another question above that. Could you explain about radio sources being polarized by interstellar magnetic field?
Okay, that's nice. So again, maybe I should just keep that sheet on. I should do that. Present now. Present the entire screen. All right. Yeah. So it's not that if a radio source is unpolarized, okay, and then the interstellar magnetic field will not have any effect on it. Okay. I do not know if whoever asked the question had in mind something else. It's true that the light from stars is by and large unpolarized. So you have a star, I'm drawing it as a disk, you know, the light is unpolarized. And that actually does get polarized by the interstellar magnetic field. So if the magnetic field is like this, right, B, then you have interstellar dust grains which have some funny shapes. And they tend to be aligned by the magnetic field. And then the dust grains also absorb the starlight. So if the dust grains happen to be perpendicular to the magnetic field, for example, this component will be absorbed more. So initially what is unpolarized becomes polarized by propagation. However, in the case of radio waves, you don't have dust grains, you don't have such things happening. But what the interstellar magnetic field can do to radio waves is, suppose the radio source is already polarized, and that can happen. Pulsars, for example, are highly polarized. That's because the electrons in the radio source are themselves moving in a magnetic field. So suppose I have a magnetic field like this, the electrons are orbiting in that magnetic field, and therefore they emit radiation which is polarized like that, right? So if a radio source itself has magnetic fields, it will emit polarized radiation. Then if I now look at the longitudinal component of the magnetic field, this is B longitudinal. So in optics, this is B transverse. Now it turns out that the refractive index of this interstellar plasma is different for the two circular polarizations, one this way and the other back. So therefore the net result is to rotate this polarization. And that is something called, I think some of you, it's called the Faraday effect. So Faraday effect is actually very useful in radio astronomy, because if you know the density of electrons here and you know how much this is rotated. Now how do you know how much this is rotated? The answer is this depends on wavelength. So theta is actually proportional to lambda squared. So you measure it, and by the way, this kind of measurement is done at GMRT also. You can measure it at a long wavelength and then at a short wavelength, and then you can find out how much the rotation is, and you can find out the magnetic field. Yeah. So there are two different phenomena here. In optics, you have aligned dust grains. Here you have a Faraday effect.
Yeah, thank you. So that was an action from you. Yeah, it says, since interference can be used to form images, does the same apply for diffraction?
See, I would not make a fundamental difference between interference and diffraction. In fact, I would rather use a single term, which is scattering. After all, whatever experiment you are carrying out, whether it be Young's double slit or single slit or anything, or a straight edge, ultimately what do you have? You have a source which is emitting radio waves or visible light. You have some distant screen or observer. And if you don't put anything here, you see the source as it is. And then everything else should be viewed as, so for example, even what you call reflection by a metal plate, I call it scattering. Right? So, and especially those of you who study quantum mechanics will know that scattering is one of the fundamental chapters. So I think this is a very unified point of view. That now, of course, in certain approximate, suppose you have a double slit, for example, then you can say that there is one wave coming from here, another wave coming from here, and then we talk of interference. But even that is an oversimplification, right? So where does the wave come from? Does it come from here? Does it come from here? A slit has got a finite size, right? So I think the most fundamental viewpoint is scattering. There is, and what I told you in the case of the single plate, namely that this electric field induces currents which in turn radiate in both directions. Is equally, after all, we don't talk about what happened in this direction, but even in Young's double slit, most of the energy goes back, right? Only a little bit gets through the slits. So I'm not making a distinction. I would say in some cases you can think of scattering as made up of interference between a finite number of paths. Then we use terms like interference. But already when we say diffraction, diffraction again you could say it's two paths. But in general I would say a scattering. So yes, you do form fringes in any case. Any other questions? I'm sorry, I'd love to see your faces, but having this blackboard in front of me, I'm not able to.
Any more questions, anybody? Otherwise, we can wind up the talk.
Yeah, I'm just sorry.
That was a great. Yeah, it was a great experience with you having for the talk. Except for the initial glitches, it was perfectly fine, and we had a wonderful insight about the field. And getting to know about the things from an experienced person like you was a great experience. And thank you for being with us and spending your valuable time.
Okay, so I'd like to say something also. I'm really sorry for this glitch, and as I said, I don't understand it. And precisely because of that, in case people really want some clarification or even references, or if you want to arrange further talks on any of this, I'll be happy to help. Anyway, since Adi is already in touch with me, that should not be a problem. Thank you very much. So is that fine? Can I sign off?
Thank you. It was a great experience. Thank you.
Okay.